Okay, we're going to find the volume of figures, three-dimensional figures, that have a known cross-sectional area. That is, if you slice it, you'll know the shape and the area of that slice. For example, very simple one, if you take a cylinder whose height is h and the radius is r. If you slice a piece, you know the radius. The thickness will be dy, and you know the radius of that slice. It's the circle of radius r with the thickness dy. So the volume will be that cross-sectional area, pi times r squared, so that slice. The volume of the slab, is the delta V, a piece of the volume, which is pi r squared times the thickness. When you integrate it, the whole volume will be the integral of pi r squared dy, and y is going, and if I had the y-axis, is going from 0 to h. 0 to h. And pi r squared is just a constant. You can think of it as being in front, and the integral of dy is just y. From 0 to h, when you plug in h for y, you get pi r squared h, and when you plug 0 in for y, you'll get 0. So it's pi r squared h minus 0, which is pi r squared. I knew the volume. I sliced this. I have a slicer like this, and I cut right through it, and the piece that I get, I know the volume of it. Sometimes that area of volume changes according to the height. For example, if you had a pyramid with a square base, and what's over the base is a little bit smaller square, and above it is a little bit smaller square. On top of that smaller square is a smaller square, and then a smaller square. So it's made up of squares that keep decreasing in size, and eventually you just get a point. That's a pyramid. Suppose, see how well I can draw this. Suppose this is your pyramid. Let's put in their third dimension. Here's your pyramid. The base is a square. Say it's b by b. And you have a height for this pyramid, h. Now, if you take an arbitrary slice, if I take this slice right here, it has some thickness to it. If I take this slice right here, I need to know that volume. Well, call each side B prime. B prime. And the thickness, since it's going up, is delta y. What I need to know is, I need to know what B prime is. So, imagine there's the y-axis somewhere. Here is 0, the very top is h, and now for some y value, this blue slice is at a height of y. So what we have is a proportion. B, the very bottom base, to the whole height is equal to B prime to the new height. Well, the new height is that distance. which is h minus y. And solving for b prime, that is just bringing this to the numerator on the other side, b prime is b times h minus y over h. But now the area, or the volume, is the base times the thickness. The area of the base is b prime squared. So if I square the left side, I have to square the right side. This is the base. I'm squaring each factor. And let's do the change in volume times the thickness with the change in h. And that's just what I need to integrate. I need to integrate b squared h minus y squared dy over h squared. And the y, the lowest rectangle, the lowest square is at height 0, and the highest one is at height h. The b over h squared can come out. This is b squared over h squared. And since we're integrating, remember, since we're squaring, a minus b squared is the same as b minus a squared. That way I can have y first. Y minus h squared dy. Well, if I call that u, then du would just be dy. If I let u be y minus h, then du would be 1 dy. Du would be dy. So we have u squared du. And remember, that's u. So what I get is u cubed over 3. I'll put the over 3 over there. And this goes from 0 to h. I'm going to think why this doesn't seem to be working. Oh, okay, it's working. So now, when I plug h in for y, I get h minus h, which is 0, cubed, which is 0, times the number in front. It's 0. Minus, now when I plug 0 in, I get b squared over 3h squared times 0 minus h cubed. Well, so this is 0 minus b squared over 3h squared. For 0 minus h is minus h, and when you cube it, you get minus h cubed. The minus in front with the minus here, because minus h cubed is negative h cubed. So it's b squared h cubed over h squared is h over 3. So there it is. And remember, the base was a b by b squared. The very bottom base was b by b. And that's the volume. Let's try to derive the volume of a cone using the fact that we know the area of the cross-sectional piece. For example, if this here is the x and the y-axis, and we have a cone that looks like this, it goes up to h, and the base radius is r, we have our we can get our proportion. If we take a slice, is going to be the area times the thickness. The thickness is a delta y. The volume is the area. Now, we need to find the radius. Well, suppose, for whatever reason, we want to put the y values here. We should put them on the y axis, but doesn't matter. Suppose that's y, and remember that's h. What we have is a proportion. We have the radius, the big radius to the big height is the little radius, call it r prime, to the little height. And that little height is going to be called y. Solving for r prime is y, or ry over h. Just bring the y up there. So that's the radius. Well, if we know the radius, we can find the volume. It's the base, pi r squared. The base is our circle. It's pi r prime squared times the thickness. But we know what r prime is. It's ry over h squared times the thickness, which is pi r squared y squared over h squared times the thickness. That's what we want to integrate from 0 to h. So the volume is, and remember, that piece right there is just a constant. It's pi r squared over h squared times the integral of y squared dy from 0 to h. The constant stays there. The integral of y squared is y cubed over 3 from 0 to h. When you put h in for y, you get pi r squared over 3h squared times not 8y, but h cubed. And when you plug in 0, you get 0. That is, here is your answer, and we can clean it up a little bit. Kill off 2 h's in the bottom and 2 h's in the top, and what you're left with is pi r squared h over 3. And that is the volume of our cone of radius r and height h. And one last comment, it's just not any old cone. It's what's called a right-hand cone. What does that mean? That means here's, say, the y-axis. The base is perpendicular to it. The base is perpendicular. That is, you have a right angle here. You can have a cone, say, that's lopsided. You can have a cone that's lopsided. It's also a cone. It's not a right-hand cone. Because if I go to the top and I come straight down, I don't hit the dead center of the cone. Here, I hit the center of the cone. So, I guess what I said was incorrect a moment ago. I said if you have this line, it's going to meet at a right angle. Yes, it's always going to meet at a right angle. But it has to hit the dead center. For example, if it was off-centered just a little bit, maybe it'll look like this. And when I drop down the perpendicular, yes, it meets with the base at a right angle, but it didn't hit the center. A right cone is when it hits the center. Here's the center. Well, let me draw it a little bit better. Here's the center. Right above it is that vertex. It goes like this. That's a right-hand cone. Okay. Maybe you can figure out what the volume would be for something like this or that, where it's not a right-handed cone. Okay, that finishes the cross-sectional problems. There aren't too many.